So the next topic is going to be solubility. This allows us to predict the miscibility if we use the term like dissolves like. So you want to think of what your solutions are. If you have two polar solutions or two non-polar solutions, they're both going to be miscible, meaning both will dissolve. However, if you have a polar and a non-polar, it's going to be immiscible. So think of oil and water, or in the previous example, you have that layer that appears. So that would be immiscible. Now, the interesting thing that happens is with ionic substances. Ionic substances will dissolve in polar things, but not non-polar things. I'm going to show you a few pictures of that in just a moment to help clarify that. So just remember a few rules about polarity and polar and non-polar. So polar things, if it has a hydroxide group, OH, it's polar. It's asymmetrical with our polar bonds. Remember the trigonal pyramid or the bent shape are considered asymmetrical. Lone pairs on the central atom. The other interesting thing here is that ionic bonds are considered polar. Non-polar things, if we have organic substances such as CH substances, it's going to dissolve. Non-polar substances, these are generally symmetrical molecules. So things like oil, lard, paint can be considered non-polar. There's actually a special compound referred to as emulsifiers. An emulsifier has a polar and a non-polar end. So the non-polar end dissolves the oil component, and the polar end will dissolve in water, making oil and water appear to mix. A common example of an emulsifier is soap. So I'm going to draw a soap molecule here. So you have usually some sort of, it can be phosphate. A phosphate is a common example here. And then you have a very long organic chain. So this is your polar end. This is your non-polar end. So most dirt that's in your clothes or on your hands are non-polar. So you need that non-polar component to help pull away the non-polar components from what you're trying to clean. And then when you use water, the water is going to take it away. So the dirt's going to be attracted to the non-polar end. So this is representing carbons and hydrogens, this chain. It's an abbreviation method for organic chemistry. This is polar. So this is our phosphate. Now, if you've ever maybe seen on TV or made soap, it used to be that after leftover lard or things like that, fat from animals, after the rest of the animal is used, would be used to make soap. They would take the fat and they'd add a few things with it to give it a polar end so that you could use it to clean. You can make soap. We could make soap from lots of oils and look at the different properties, but unfortunately we don't have time. So here I have an example. This is sodium chloride. The white spheres are my sodium ions, and the green spheres represent the chlorine ions. So what ends up happening when this is placed into water? The water molecules are going to surround them. Now remember from our previous unit, the hydrogens are going to be partially positive and the oxygens partially negative. So what's going to happen is the water is going to surround each ion and pull it into solution. So here notice the hydrogens are attaching or are pulling away the chlorine here, and over here the oxygens are pulling away the sodium. Now something you can kind of use to help you visualize this as happening is you can think of the ions as sheep and the water molecules as wolves. The water molecules surround and pull each into the solution in order to dissolve it. So this happens over and over again. Water molecules pulling away each ion until there's only a few left, and then there's none left. The solubility of a solution dissolved in 100 grams of water is tested at many different temperatures. The amount of grams is plotted on a graph based on the saturated solution. So this used to be an experiment that we did, but it's not very exciting. What you do, you dissolve a certain amount of solute and you at a certain temperature to figure out how much water and how much solute is necessary to do this, and then you graph it. So the line represents your saturated solution. So I'm going to represent that as a red here. Now it should be exactly on the line to be my saturated solution. Below the line, so all of this area represents my unsaturated solution. So we connect them with a line or a curve. It represents the maximum amount of a solute dissolved in 100 grams of water for all temperatures between 0 and 100 degrees Celsius. Keep in mind, we only go from 0 to 100 degrees Celsius because this is where we have a liquid. For water, if we go beyond those, we don't have a liquid anymore. So then a supersaturated solution's made by heating the solution and adding the maximum amount of a solute and letting it cool. So let's think about this. I'm going to do this in green, I guess. Okay, so let's pretend we are at room temperature and we dissolve this substance, and it can only hold about 30 grams. But if we heat it up to 60 degrees Celsius, it now can hold 60 grams. So we add 60 grams. If we then let it cool back down to 20 degrees Celsius, 20 degrees Celsius now holds 60 grams. This is why it's unstable. It really shouldn't be able to have those 60 grams, but it can because of the process. So because it's a bit unstable, it doesn't take much for crystallization to occur. Have you ever seen those, like their heat packs that they are clear and then there's a button inside and they turn white and get really, really hot? I used to have one, but it broke. But that's an example of a supersaturated solution, because then once you hit the little button, it causes rapid crystallization and releases the heat for your heat pack. For any point on the solubility curve, the solution is saturated. For any point below the solubility curve, the solution is unsaturated. Now, I know it doesn't explicitly say this, but any point above the line is impossible. You can't just have a supersaturated solution. What will happen is you'll be able to dissolve up to the line, and then the rest will remain at the bottom undissolved. So it's impossible to dissolve above the line unless you're following the pattern of a supersaturated solution. So here's a few example questions of things you could see. So at 40 degrees Celsius, 100 grams of water can dissolve how much solute? So taking a look at our graph, we would find 40 degrees Celsius, and we would estimate that this would probably be about 44, 45 grams of solute. So I'm going to say 44 grams. Normally you would know what the solute is, but on this particular graph it doesn't tell you that. Will 50 grams dissolve in 100 grams of water at 75 degrees Celsius? So again, you go to the graph, you find approximately 75 degrees Celsius and 50 grams, and it looks like it will pretty easily dissolve. So at that point, where was it? 75 and 50. You can probably dissolve up to 80. So this will. So you would say like, yes, can dissolve up to 80 grams. And then will a solution with 70 grams of solute dissolved at 40 degrees Celsius be saturated, unsaturated, or supersaturated? The key to this problem is it tells you it's already a solution. You have a solution, it's already made with 70 grams of solute at 40 degrees Celsius. So 40 degrees Celsius is right here, 70 is up here. So since it's already a solution, it would be supersaturated. Now, if it asked you to make the solution, all you could do would be have it be saturated, or you would have to describe the process to make it supersaturated. So here's an example of a more common solubility curve. This is usually what you see. It's usually a bunch of substances together, and you have some questions about them. So I want you to try this on your own, and we'll go through it together when you're done. So for question number 1, there's actually multiple answers here. All you know is that 25 grams is dissolved at 60 degrees Celsius. So you might be tempted to say KClO3, but if you look really closely, it's actually below the line, but it's really any substance above this. So definitely not the this bottom one. So really anything but the Ce2SO4. So this is a unique substance that the solubility decreases. Generally only gases decrease, but in this case this substance decreases as well. If 50 grams of KCl are dissolved in 100 grams of water at 80 degrees Celsius, is the solution saturated, unsaturated, or supersaturated? So the key here is it's a solution that's made, it's dissolved. We have 50 grams of KCl at 80 degrees Celsius. So this 50 degrees is right below where the line is. That results that this is a unsaturated solution. What is the solubility of KNO3 at 45 degrees Celsius in 200 grams of water? So 45 degrees Celsius, we would find that on the graph of KNO3. It looks to be about 75 grams, but keep in mind that's for 100 grams of water, so we're going to have to double it. So we're going to multiply it by 2 and we'll end up with 150 grams. Generally speaking, these questions are multiple choice. So sig figs aren't really an issue here, but because if we wanted to make sig figs accurate here, we would have to put a decimal place. And then the last one, what is the solubility of NaCl at 99 degrees Celsius in 50 grams of water? So we would find NaCl at 99, which it looks to be about 40 grams. So 40 grams of NaCl in 100 grams of water, which isn't what we want. The question was asking for 50, so it would be about 20 grams of NaCl in 50 grams of water, or 50 grams of water. So you can try the remaining problems here on your own.